Hello everyone, this is Lef Loannidis. I'm a software architect at UnifyID. I'm here to talk to you about NGINX and machine learning, an interesting, promising combination. So UnifyID is doing implicit authentication, so we're trying to revolutionize authentication, try to get rid of passwords by using kind of what makes the user unique, running machine learning on all kinds of data that we get from commodity devices like smartphones, computers. Just from your walk, we can tell with pretty high accuracy if it's you versus somebody else, just from the way you walk while having your phone in your pocket. So naturally, we're trying to do a lot of real-time machine learning on data that we get from thousands of users. So performance is very important to us, accuracy is important to us, being real-time is very important to us. So I'll show you how we use NGINX to accomplish those goals. Today we'll talk about why we should use microservices for machine learning and why we shouldn't. I'll talk about statefullness, which is a very big factor for machine learning because machine learning is very stateful. Sources of latency that can come from that. I'll show you how you can design pipelines for deep learning and sources of latency that come with that. And then we'll show you a new open source project that we started called WebTorch, and there will be a live demo. Cool. So almost a year ago, we published a blog post about why you should be doing your machine learning in production using microservices. And everything we said was completely wrong because it turns out machine learning is very stateful, and as you can see, every single factor that we're processing, for example, if you have a facial recognition factor, that has its own state, symbolized by the DB. And if you're doing a gate analysis, like I showed you in that GIF, that uses its own state. And if you're just doing auto-scaling using elastic beanstalk, which is what we had in our original implementation, that turns out to be very costly because of context switching. So you need to be loading and storing those models all the time. Not really great. Also, there's a lot of communication overhead because we're talking about a lot of data being streamed from the gateway to the services. And just serialization, queuing of the data, processing, deserialization can take a long time. So why is ML so stateful? All right, so let's see the anatomy of a neural network. It has some inputs, hidden layers, and outputs. And the amount of state that you need to store is multiplied quadratically with the width of the network. So as you can see, even a very small network with 3 inputs and 1 output can have a pretty large state, which is signified by this matrix. Actually, the matrix and the vector. So those are the weights of the neural network. Not only is that a lot of floating point numbers that you need to keep track of, these get updated very often. So context switching is not an option here, storing and loading the model just to do incremental updates. Using deltas to do updates is also not optimal because one change in the first weight will propagate all the way down to the neural network. So that leaves us very few options. Yeah, just to give you an example, the MNIST neural network, which is a set of data for classifying handwritten digits in people's checks, for example, is 47 megabytes. And the ResNet, which is a network for identifying cats, is 170 megabytes. So sources of latency while context switching. You need to serialize your neural net. You need to serialize to some database format. Unfortunately, so far we're not aware of some great database that can store neural networks or any kind of like graph data structure and allow for incremental updates without taking forever. I/O can be very expensive as well. Unloading the model from memory, this is all stuff you need to do when context switching. And same when you're storing a model. You need to read from I/O, load the model in memory, deserialize it, make it to some tensor format or some matrix format that your runtime can actually use. All of those very expensive operations. So one way we got around this is by using a cool feature of NGINX Plus, which is sticky sessions. So what is sticky sessions? Has anybody used sticky sessions here before? All right. So you guys know what it is. Basically, I can serve a cookie to my clients, and then using that cookie, they will always end up in the same machine. That's awesome because now the model lives in that machine forever, and it doesn't need to be loaded and unloaded. You always hit the cache, you always hit the memory. You skip all that serializing, deserializing, and loading and unloading. So that's a really awesome feature of NGINX Plus that I would really recommend to use it if you're writing load balancers for machine learning. And this is an example of how we are using it. We have a registration microservice. When a new source of data shows up, it registers, it gets a cookie, and then it ends up going to a specific backend. So in my example, I have 2 TensorFlow backends and a Torch backend. Those can be different machine learning algorithms or the same. What matters is that the same model will stay in the same machine, same virtual address if you want to do it even more sticky in the virtual address kind of level. So that's one problem solved. We'll talk about how to design a pipeline for deep learning. It's actually way more involved than just having single services. Sometimes you need to do a lot of things. Things like processing the metadata, what kind of data are we talking about? Cleaning and filtering, there's outliers, you need to do some outlier detection, there could be some adversarial metadata in there. All of that stuff we need to clear. Then you need to do feature extraction. Usually raw data cannot be directly fed into a neural network. You need to do some feature extraction for that. And then deep learning. So there's multiple stages to that. And like I said, thinking in microservices, in the beginning we decided to do everything as modular as possible. So every one of those stages, think of it as a microservice. So what's the problem with that? Any ideas? There's a lot of inputs, right? There's a lot of traffic going on. So that incurs a lot of latency between those stages. So between the metadata and the cleaning and filtering stages, you're probably streaming a lot of data from one service to another. If that's just plain old HTTP services, we're talking about serialization, compression, maybe encryption. For example, if you're using Kubernetes in production and you want to do end-to-end encryption, you're going to be encrypting all your data from service to service using using TLS that Kubernetes uses implicitly. Then there's transport and there's queuing, which can be either explicit if you're using a data queue, something like Kafka or MQTT, or it can be implicit, just the network queue. All of these very expensive operations. And same as when data are incoming, you need to dequeue it, decrypt it, decompress, and deserialize in some useful format. Yeah, how to solve this problem? A kind of crazy solution that we came up with is, what if we could just run all of this pipeline in a single process, single virtual address space, exactly the opposite of microservices. But that will serve as an example to show, how much of that stuff do we actually want to modularize, and how much of this cost we're actually willing to take. Still an interesting experiment. So going down that road, we figured out that NGINX and Torch, a very popular deep learning framework, have one thing in common, which is the Lua JIT. So has anyone here used the Lua features of NGINX? Awesome, all right. So the Lua JIT is, it's actually a very fast JIT. It can write very fast code, and it can be dynamically or statically linked to NGINX. Torch, on the other hand, is also a static library that you can write your code and link it with Torch, link it with NGINX, have a module that can be loaded on both things. And this is exactly what we did. We built Torch with Lua JIT rocks, which is the recommended way. Not the recommended way to build Lua JIT for NGINX, however. Actually, everything we did here is not recommended by NGINX at all. So we statically linked those .so libraries, set the paths, build the NGINX tarball with the Lua NGINX module and the NGINX dev kit, the NDK. And we dynamically linked using content by Lua file. That's one way to do it using dynamic linking. You can also do static linking, which is all the same stuff, but you build the Lua JIT bytecode as a static library, and then you build NGINX with your module in it. That's obviously faster and better because now anywhere inside the NGINX namespace, you can have Torch, you can have your neural net, you can have your functions, your tensors, anything you want is visible inside the NGINX process. All right, so let me try to do a live demo here. I hope this will work. All right. So what we have here is we have a container of WebTorch, which is the alpha version of our server, which is which combines NGINX and Torch, and I'm going to try to build it. So that will build NGINX. That will build our code here as Lua bytecode. So I have 3 files: one for training the network, one for outputting the results of the network, and an initialization step. So all of those are built into modules, and now let me run it. Let me listen to port 3000. All right, let's see. Okay, so presumably now NGINX is running. Let's make sure. I'll just curl it a little bit. All right, so it is running. That's not super interesting though. What's really interesting is when I start training it. So I'm training with random numbers. So let me tell you exactly what this demo is. I'm using something called the XORnet, which is basically training a neural network to learn the XOR operation. I'm giving it 2 floating point numbers, just completely random. I'm XORing them and feeding it the result in the training phase, and then I'm feeding it the same numbers, 0.5 and 0.5, and see if it can predict the result without really knowing what the XOR operation does, but if it can learn it. So that's what I'm gonna do here. So every time we do a GET request on train, it's gonna give it 2 random numbers. It's gonna give it 0.2, and then to figure out if we actually trained the net, I'm gonna do a GET operation on the output endpoint. Okay, so 0.5 XOR 0.5, it's not minus 0.78, so it's close. Let me try to train it a little bit more. Or I can do actually a benchmark. I also have a post request, which I can just send it numbers, and I have a script, a rec script, which is actually just a serialized vector with 2 floating point numbers, which are random, and I'm just gonna spam the server with it as much as possible using the rec tool, which is also written in Lua. So that was a happy coincidence. Let's see. So this is gonna use 12 threads and 400 connections for 30 seconds using the script I just showed you, which is just spamming random numbers on the train endpoint. Make sure, my server is definitely listening, so let's see. It's far away. All right, boom. Okay, so we're getting requests. It's gonna last for 30 seconds. Let's see how many requests per second we can get. And a reminder, this is running on my MacBook Air, not even the latest one, and it's not using GPU acceleration. It's running real Torch and a real neural network, but everything on CPU. So the results you're gonna see are pretty much the worst results you can get. But I hope this is still gonna be pretty good in order to convince you that. Oh, there we go. So we managed to get 1,041 requests per second on a real neural network, just on my MacBook Air. And indeed, if you try to curl on localhost on the output port, yeah, so that gives better results because we trained a lot more. So I hope that I convinced you that the performance of Torch on top of NGINX is pretty good. There's a lot of challenges to make it even better. So let me talk about that. Let me talk some things we did and some things we're gonna need to do in the future. Also, yes, we're gonna open source this demo that you just saw, and we're gonna make an API out of it so people can actually use it. The purpose is rapid prototyping from data scientists or machine learning people. Hopefully anyone can download our server, have some examples, have some documentation, write a little bit of Torch code, and it becomes a scalable server you can deploy easily, single process NGINX with Torch, and you can deploy and scale independently. The timeline we have for this is over the next 4 months. We want to make it, so far it's just a Docker file and just a beta, which is really an alpha. And then we need to write the CMake, write some serializers for like various types of inputs. So things like CSVs or JSON, maybe protobuf even. Refactor the API a bit, make it better looking, and then work on performance, which I'll talk about why that's important. Documentation and examples for last. So yeah, keep an eye on this repo. Watch it if you want on GitHub, if you're interested in something like that, and we're interested in getting open source contributors too. So talk to me after if you're interested in that. Cool. So let's talk about the details of this. One problem we had is that every request on NGINX is its own memory. So there's no shared memory between requests. To do that, you need to use something called the NGINX share model. This is basically a memory which is shared across threads. And the problem is that it's locked. So you need to, when you're reading from it or writing to it, every ngx.shared.anything is gonna lock. So that's super dangerous. Still not bad though, like 1,000 requests per second. That's what we're using right now. We need a better way to do concurrent reads and writes, but that's what we have, the solution we have so far. Another issue is that NGINX was not built for this. Not at all. Actually, it was built for short-running tasks, running across multiple threads in a thread pool, not really long-running blocking machine learning jobs. In this diagram that I stole from the NGINX blog, you can see that if I have 2 threads, right, and I have 2 machine learning jobs running on this, and they're both long, all my threads are going to block. I'm not going to be able to serve any more requests. A better way to solve this is to have 2 different classes of threads. One thread pool that serves requests, and one thread pool that does machine learning. And one is long running, the other is short running. So like the blocking of the machine learning doesn't affect how the HTTP server works. So that's more of a design that will help for this problem. So in that example you saw, I was using Torch tensors, which have their own native serialization format. Super easy to use. You can just call serialize and you get a string, and you deserialize and you get an object. Other serializers we want to use is CSV, which is something that people are really used to. A lot of data science people are really familiar with the CSV format, same as JSON. The optimal thing in terms of performance is protobuf, because it's all about minimizing the size of the packets. So all of these are things that we'd be interested in implementing. So like I said, my laptop is probably the worst performance you can get, and here's the proof. I ran some pretty big ResNets on GPUs, and the performance we get in milliseconds is staggering. So less than 45 milliseconds for Inception v1, which is a lot of layers, on a Pascal Titan X. Even on a GTX 1080, you get close to 45 milliseconds. And for ResNet 50, which is 50 hidden layers, a pretty big network, more than 100 megabytes in size, you can serve a single image, train on a single image in 135 milliseconds. So this is pretty great performance from Torch. Important detail, it's using CUDNN. CU stands for CUDA. So this is running CUDA code, which is why we're getting 1 or 2 orders of magnitude better performance than CPUs. I don't know if you're willing to run NGINX on CUDA, but hey, why not? So here's some applications, right? Like we brought 2 things which were completely separate together. We brought load balancers and machine learning together. And that can create some interesting applications, right? Like we can classify streaming data in the load balancer. We could do adaptive load balancing, use machine learning to figure out what to route where. We could protect against DDoS, intrusion detection, all of those things. We can even use GPU code on the load balancer to solve load balancing problems, which can be great because Torch is already GPU enabled, and now NGINX can be too. And of course, the most important thing and the goal of WebTorch is the rapid prototyping of machine learning solutions. If you're a data scientist, we want you to be able to just write Torch code, write something that you're familiar with, and serve it super easy. Don't waste more time to make it scale. Yeah, and that's all. We would like to see some of you come and visit our repo and maybe express interest or file issues. Yeah, and if you have any questions, please come find me. Yes?
You transfer a model. So once your training has happened on a single node, how do you export the model and bring it into the fewer repositories?
Yeah, so we didn't build persistent yet on it, but you will need to do something like there's a way to serialize a torch model. So you need to serialize and then dump it on a file or a database or something.
Any motivation to do like online learning across all the nodes?
Online learning across all the nodes, as in make it like distributed. That has the problems that I mentioned at the beginning of context switching. Some people have done some crazy solutions like Jeff Dean's distributed layering, like in TensorFlow. Basically, he's running one layer on a separate machine.
I meant more like sending the training to all the nodes and then only classifying on one node. So you load balance for classification. The training is across the node.
I see. Same data or different data? Yeah, you could do that. You could just horizontally scale it as much as you want. I don't see any problem with that. Questions? Yeah.
You mentioned sticky sessions. What happens if the host dies?
Yeah, good question. You need to use something that gives you availability, something like Kubernetes or something that can ensure that, okay, I'm going to restart the container, I'm going to restart the host.
So you're running a container solution.
Yeah, there's no other way, but you have to context switch, right? If it dies, then the model is dead. There's no saving it. And that has some performance overhead, so yeah. Yeah.
If you're using any thread pool to process algorithms, because I assume that some algorithms cannot have concurrently on the same thread, right? Did you have this problem so far?
What was that?
Concurrency problem.
As in like race conditions, or in what way? Like performance-wise?
It's like when, for instance, you can't run an algorithm on the same, like two algorithms concurrently on the same thread.
So define threads, because I think NGINX uses light threads, which are different than your traditional like threads. But because the NGINX.shared memory model is locked, we didn't have these problems because you lock it, you read it, you unlock it, and then you lock it, you write it, you unlock it. So that kind of ensures that there's no race conditions. Ideally, what you would want to do is only lock the part of the model that you want to update, or like somebody said, like be able to distribute the model. Yeah, but we're not there yet. Definitely, that's something that we're looking into.
Follow-up question.
Yeah.
Did you load like bigger models to keep the memory limitation, which I think is 2 gigabytes?
So yeah, great question. It's actually way less than 2 gigabytes. The shared memory you can use, but I think there's an option on NGINX you can use to set it to as much as you want. For this demo, I set it to 10 megabytes of shared memory. With Logit, I don't think I had the problem. Like I was able to load the ResNet 50 on like native Torch and didn't complain really. And I think because it could be because I'm using the Torch Logit, which is already built for big models, to compile my NGINX. So maybe I got like a free lunch. Any questions? Sweet. Thanks so much for coming.